All right, let's get into something that sounds like it's straight out of science fiction. We're going to be talking about a brand new technology for creating a single material that has two completely opposite personalities. And get this, it's engineered using just a blast of light.
So that brings up a pretty mind-bending question, doesn't it? How on earth can one surface love and hate water at the exact same time? It seems like a total paradox. How can one tiny spot repel water while the spot right next to it just soaks it up? Well, that's the big question we're going to tackle today.
And to figure that out, we're going to do what scientists so often do. We're going to look for inspiration from the natural world. I mean, nature's been solving these kinds of crazy problems for millions of years. Okay, so it all boils down to these two key ideas. On one hand, you have superhydrophobic surfaces. You can just think of that as water-fearing. These are surfaces that hate water so much that droplets just beat up into these perfect little spheres and roll right off. And on the other hand, you have superhydrophilic surfaces, or water-loving, which cause water to immediately spread out in a super thin film.
And this visualizes it perfectly. You can actually measure this property using something called a water contact angle. So see that high angle on the left? Over 150 degrees? That creates that perfect round bead of water. That's our superhydrophobic surface. But then you look at the right, and that super low angle, less than 20 degrees. That's what makes the water flatten out and spread. That's superhydrophilic.
And you know what? Nature has totally mastered this. The lotus leaf is the classic example of a superhydrophobic surface, which is how it stays so clean and dry. Then you have shark skin, which actually uses water-loving properties to reduce drag so it can swim faster. But the real genius here is the Namib desert beetle. It has a pattern of both on its back, and it uses it to literally pull water out of the air to survive. Talk about a natural blueprint.
So the big question is, how do we copy that in a lab? Well, it turns out you need two key things: a really special molecule that kind of has a split personality, and a very unique material to act as our canvas. And the scientific word for this two-faced property is amphiphilic. It just means a material that has both water-loving and water-fearing parts built right into its DNA, so to speak. This one concept, this is the key that makes everything else work. Now, to build these surfaces, scientists use this really powerful and efficient process called thiol click chemistry. The name sounds complicated, but you can just think of it like molecular Legos. It's a super fast, super precise way to just click different chemical properties into place, exactly where you want them. And this is our canvas. It's a material called anodic aluminum oxide, or AAO for short. Now, the crucial thing to see here is that this isn't some flat, boring surface. It's this amazing three-dimensional landscape of microscopic pores, all packed tightly together. That porous structure gives us a massive amount of surface area to play with.
Okay, so we've got our chemical toolkit, and we've got our nanoscale canvas. Now for the really cool part. Let's see how it all comes together when we use light to literally paint these properties right onto that surface.
You know, the process itself is actually pretty clever and straightforward. First, they apply a chemical solution to the membrane. Then, they place a photomask on top. It's basically a tiny stencil. They hit it with a blast of UV light, which triggers a chemical reaction, but only in the areas that aren't covered by the stencil. Then, they take the mask off, apply a second chemical solution, and hit it with one final blast of UV. And just like that, you've got a permanent patterned surface with two distinct personalities.
And here's the proof that it works. This graph is tracking the water contact angle during the process. Just look at that green line. Shooting up towards 150 degrees, that's the surface becoming more and more water-fearing. At the same time, the purple line just plummets down to 20 degrees, becoming super water-loving. And the craziest part? This entire transformation happens in just 5 minutes.
And that right there is what makes this so important. The researchers who developed this even say it in their paper. This method isn't just some cool experiment that only works in a high-tech lab. No, it's designed to be practical. It's fast, it's relatively simple, and it's affordable. And that's absolutely crucial if you want to turn a scientific discovery into a technology that people can actually use.
So great, we can make these incredible patterned surfaces. But what do we actually do with them? Well, this is where the story gets really exciting, because the applications here could change everything from security to electronics. First step, a new generation of security tags that are basically impossible to fake. Why? Because the pattern isn't printed with ink or something you can scrape off. It's literally baked into the chemical nature of the material itself. Oh, this is just awesome. On the left is the little mask they used for the pattern.
Now, if you look at the finished material with your own eyes, it just looks blank. But, as you can see on the right, as soon as you add a drop of a very specific solvent, poof, the hidden pattern magically appears. The solvent is only attracted to the water-loving parts, which reveals the invisible information. How cool is that?
Okay, the second big application is just as revolutionary. We're talking about creating incredibly precise conductive pathways, which could be a game changer for flexible and other advanced electronics.
So here's the key. Those water-loving hydrophilic regions, they act like microscopic channels. So when you apply a conductive silver paint, it naturally just flows into and sticks only to those channels. You're basically letting the surface chemistry draw the circuit for you with unbelievable precision.
And just look at the result. This chart is wild. It shows the electrical resistivity. That giant bar on the left, that's the raw material. It's a powerful insulator. Electricity can't get through. But that tiny little bar on the right, where the silver paint has created a pathway, the resistance just plummets. I mean, it's a mind-boggling drop. It becomes an excellent conductor. That's literally the difference between a brick wall and a copper wire.
So, let's wrap this all up. What this research really shows us is that we now have a way to precisely control a material's behavior at the tiniest scales imaginable. This unlocks brand new types of security tags and opens the door to a much smarter way of building electronics. And maybe most importantly, the material itself is tough. It's stable, it's durable, and you can even reuse it.
Which really just leaves us with one last big question. We've just seen how we can give a material some pretty simple instructions. Attract water here, repel it over there. But as this technology grows, what other, more complex instructions could we one day embed into the very fabric of the materials that build our world?